Imagine a material not found in nature, not mined from the earth or grown from a seed, but designed, atom by atom, structure by structure, to do the impossible. This is the world of metamaterials. They aren't special because of what they're made of, often just simple plastics, metals, or ceramics. Their magic lies in their intricate, repeating patterns. These tiny, engineered structures, smaller than the wavelength of light or sound they are meant to control, give them abilities that defy our everyday experience. They are a testament to human ingenuity, a way for us to write new rules for how energy and matter interact. Think about the materials that surround us. A piece of glass is transparent because of the way its molecules are arranged. Gold shines for the same reason. These properties are inherent to the substance itself, a gift from the cosmos. But metamaterials are different. Their properties come from their architecture. Scientists become like cosmic architects, designing tiny lattices, rings, and posts. By carefully arranging these structures, they can create a material that bends light backward, makes an object invisible to sound waves, or even absorbs energy with near-perfect efficiency. It's a fundamental shift in how we think about stuff. The universe is governed by physical laws, rules that dictate how light bends and how sound travels. Metamaterials don't break these laws, but they do find clever loopholes. By controlling the shape, size, and orientation of their internal structures, scientists can guide waves in extraordinary ways. This allows them to create materials with a negative refractive index, a property that doesn't exist in any naturally occurring substance. When light enters such a material, it bends in the opposite direction from what we expect, opening up a universe of possibilities that nature itself never explored. This journey into metamaterials is a journey into the unseen. It's about manipulating the very fabric of perception. What if you could design a surface that perfectly absorbs all sound, creating a zone of absolute silence? What if you could craft a lens so powerful it could see details smaller than the wavelength of light itself, breaking a long-held barrier in optics? These aren't just thought experiments. They are the tangible goals that scientists are pursuing today. We are no longer just discovering the materials of the universe. We are inventing them, stepping into a new era of creation. So how do scientists build these fantastic materials? It begins on a computer. They design a unit cell, the basic repeating block of the metamaterials structure. This tiny element is meticulously engineered to interact with a specific type of wave, be it light, sound, or even heat. For instance, to manipulate light, the unit cell might contain a tiny metal ring that resonates when electromagnetic waves pass by. This resonance disturbs the wave, altering its path. By arranging millions of these unit cells into a precise, repeating grid, the material as a whole gains a new collective property that none of its parts possess alone. Consider the quest for a perfect lens. A conventional lens, like the one in a camera or a microscope, is limited by something called the diffraction limit. This physical barrier prevents us from seeing details smaller than half the wavelength of light being used. But a metamaterial lens, designed with a negative refractive index, could overcome this. It can capture and refocus the evanescent waves, the fine detailed information that decays quickly and is lost in a normal lens. By restoring this lost information, such a lens could give us an unprecedentedly clear view of the microscopic world, from the inner workings of a living cell to the delicate structures of a virus. Another amazing application is the creation of special surfaces, known as metasurfaces. These are extremely thin, two-dimensional versions of metamaterials. Imagine a sheet of material, almost invisibly thin, that can control waves just as effectively as a bulky, three-dimensional object. A metasurface could replace a thick, curved glass lens with a completely flat one, leading to radically thinner cameras and optical devices. Or it could be painted onto a surface to make it selectively absorb or reflect certain frequencies, creating advanced sensors or stealth technology that can hide an object from radar. The possibilities are as vast as the surfaces we can coat. This process of design and control allows us to play with waves in ways that were once pure science fiction. We can create acoustic metamaterials that steer sound around an object, effectively making it silent. These invisibility cloaks for sound could shield a hospital room from outside noise or protect a submarine from sonar detection. The key is always the structure. By building materials with a specific geometric pattern, we are essentially telling waves where to go and what to do. We are becoming masters of the unseen forces that shape our reality. The next great leap forward for metamaterials is intelligence. The first generation of these materials had fixed properties set by their initial design. But what if a material could change its properties on demand? Scientists are now creating tunable and switchable metamaterials that can adapt to their environment or respond to a user's command. Imagine a window that can switch from transparent to opaque, or a lens that can change its focal point with the flick of a switch, all without any moving parts. This is achieved by incorporating elements that respond to external stimuli like electricity, heat, or light. One of the most exciting new frontiers is the concept of coded or digital metamaterials. Here, the unit cells are designed to have a limited number of states, like the zeros and ones of computer code. A cell might, for example, either reflect a wave or let it pass through. By arranging these binary cells in a specific sequence, scientists can program the material's function. This allows them to create a single metasurface that can perform multiple tasks, like scattering a beam of light into a complex holographic image or steering a Wi-Fi signal directly to your device. It's like turning a static piece of matter into a programmable information processor. This ability to program matter opens the door to new forms of computing. Instead of using silicon chips and electrical currents, we could one day perform calculations using waves of light or sound as they pass through a carefully designed metamaterial. These photonic or acoustic computers could process information at incredible speeds, using far less energy than today's electronics. The metamaterial itself becomes the computer, with its structure acting as the hardware and the incoming wave acting as the software. This represents a paradigm shift, moving computation from electronics into the very fabric of physical objects. Furthermore, scientists are exploring topological effects in metamaterials. In simple terms, topology deals with properties that remain unchanged even when an object is stretched or deformed. By designing metamaterials with specific topological properties, we can create pathways for light or sound that are incredibly robust. These pathways are protected from scattering or disruption caused by tiny imperfections in the material. This means we can build more reliable and efficient devices, where energy flows exactly where we want it to go, without loss or interference. It's like creating a perfectly smooth, protected superhighway for waves. The implications of these advancing trends are profound, promising to reshape the technologies that define our modern world. Think about the devices you use every day. Your smartphone camera has a complex stack of curved lenses to focus light. A flat metasurface lens could make it dramatically thinner and lighter. The antennas that provide your Wi-Fi and 5G signals could be replaced by intelligent metasurfaces that actively steer beams to improve your connection and reduce energy waste. Our interaction with the digital world, with light and with sound, is on the verge of a fundamental transformation, all thanks to these engineered materials. In medicine, the future looks even brighter. Imagine ultra-high-resolution imaging that allows doctors to see inside a single cell without damaging it, thanks to perfect lenses. Or consider non-invasive surgery, where focused ultrasound, guided by acoustic metamaterials, can target and destroy tumors deep inside the body with surgical precision, leaving surrounding tissue unharmed. Wearable sensors made from flexible metamaterials could constantly monitor vital signs with unparalleled accuracy. These are not distant dreams. They are the direct applications of the science being developed in labs right now. Even our relationship with energy could be redefined. Metamaterials designed to absorb light with near-perfect efficiency could lead to a new generation of solar panels that capture far more of the sun's energy. Other materials could be engineered to harvest ambient radio waves from the air, providing a way to wirelessly power small devices and sensors. We could even design thermal metamaterials that precisely control the flow of heat, leading to hyper-efficient insulation for buildings or advanced cooling systems for computers. We are learning to manage energy with a level of control that was previously unimaginable. As we stand here, on the 1st of December 2025, we are witnessing the dawn of the metamaterial age. We have moved from being discoverers of nature's materials to being their architects. From programmable matter and wave-based computing to hyper-efficient energy and revolutionary medicine, the scope of what is possible is expanding at a breathtaking pace. The journey of metamaterials is a powerful reminder that the cosmos is not only full of wonders to be discovered, but it has also given us the tools, our minds, our curiosity, and the laws of physics to create new wonders of our own. The future is not just something we will arrive at, it is something we will build.